Welcome to Study Loop.
Oxyhemoglobin with an O2 bound to iron is a low-spin iron 2 complex. Deoxyhemoglobin without the O2 is a high-spin complex. For part A, how many unpaired wait, let me try this again. Assume that the coordination environment about the metal is octahedral. How many unpaired electrons are centered on the metal in each case? Okay, there's A. The electron configuration of Fe2 plus is as follows. The low spin complex has 0 unshared electrons. Let's take a look at this. I'm going to switch these colors. Okay, there's my first. This is for the oxyhemoglobin. And the deoxy is as follows. And those will look like, let's do those in green. Will look like that. And blah, blah, blah. How many unpaired electrons? So this has 0 unpaired electrons. And this has 4 unpaired electrons. Okay, part B. What ligand is coordinated to the iron in place of O2 in deoxyhemoglobin? Okay. So in deoxyhemoglobin without oxygen, let me see if this is what they're asking. What ligand is coordinated? I've got the sixth coordinate, the sixth coordination point is empty. Part C. Explain in a general way why two forms of hemoglobin have different colors. When the oxygen binds, I got to get all my stuff showing here. When oxygen binds, let's switch different colors here so you can see. The Fe and O2 orbitals bind. They bond and their energies change. The iron changes from 2 plus to 3 plus, and the geometry becomes octahedral. The ligand pairs interact with the electrons in the d orbitals of iron. The repulsion raises the energy difference between the d orbitals of iron. The deoxygenated conformation of hemoglobin absorbs light in the orange range and reflects blue light. So the deoxygenated conformation of hemoglobin is the blue color. Okay, you can read that. I don't need to read that to you. Good Lord, there's part D in here too. Okay. 15-minute exposure. To air containing 400 part per million CO causes approximately 10% of the hemoglobin in blood to be converted into carbon monoxide complex. Which is called, where is it? Carboxyhemoglobin. What does this suggest about the relative equilibrium constants for binding of CO and O2 to hemoglobin? That was crazy just to write the question down. Let's go red. Carbon monoxide has a much greater affinity for hemoglobin than oxygen. One more. And I'm going to go to one more page for this. CO is a strong field ligand. What color might you expect carboxyhemoglobin to be? Okay. It's a strong field ligand. Colored compounds absorb light, and I'm going to specify that that's visible. And this absorption is responsible for color. And we see the complementary color. Of what is absorbed. CO is a stronger field ligand than O2. So the carboxyhemoglobin will absorb a shorter wavelength than hemoglobin. So hemoglobin, we said, absorbs green, blue-green, so the carboxyhemoglobin will absorb something a little above that, maybe blue-green or blue, and will appear probably in orange-red. Orange or orange-red. Finally, we're done.